Yeah, I put this on. There you go.
Yeah, so we're going to be presenting PWN II, continuation of PWN I, where we were exploring our workflows. So, right, yeah, this is the meeting flag. I'll give you all a minute to do this.
Maybe more than
and this is a little hint as to what we're going to be talking about today. These kind of strings. So, in this case, it's kind of funny because it just bricks Wi-Fi on iOS, but we could do a little bit more interesting stuff as you'll see in a little bit. All right, we can come back to this later because it's like a lot of specific characters to type, but yeah, so let's just do like a quick review of what we talked about in PWN I. So like buffers and variables that are like local to the functions are stored on the stack at a fixed size, and they're just laid out sequentially in contiguous memory. So that means that if we have some unsafe code that might go over the size of the variable, or like a buffer and a memory on a stack, we can actually go beyond that into other variables on the stack. And then eventually, if we keep going down the stack, we'll get to the return address, and we can modify that in order to take control of the program execution. So when the function returns, we'll jump to our attacker controlled address. So shellcode is just a term for like instructions that we have that we'd like to execute in order to do something. So most common case that you'll do here is you'll launch a shell, as the name sort of implies. So you can try to write your own, or it's probably a lot easier to just Google existing ones because there's been like a lot of people who like try to get these shorter and shorter. So like for instance, we have this link to one of them. You can just search for like x86 shellcode, you'll find something. So the ones that we're talking about here, they'll just open a shell when you execute the instructions. But you can do a lot of other things. So you could like write to files, allocate memory, stuff like that. So like this is how you might use your shellcode. So let's say like you have this dangerous function gets that will overflow this if you provide more than 8 characters. If you do like more than 8 characters, it will eventually overwrite the return address, and then you could point it to your shellcode so that your return address will point to the bytes that are your executable code, which will execute your target program. So one mitigation for this, as you saw earlier, we're placing our shellcode in the payload, which would be put onto the stack. So what we can do is say, well, these are variables, right? Maybe they're not code, so we shouldn't be able to execute them, right? So this kind of exploit only works if the memory that you place your shellcode into is executable. So what you generally would have is write XOR execute, which means you either can write to that memory or you could execute it. So you can't do both. So in modern programs, you'll only have read and write permissions on stack variables because that's what you normally do with variables, right? You're not putting code in there, hopefully. But back in the day, this wasn't considered, and you could do like executable code on the stack, which is what you see in kind of a lot of older exploits. So you'll learn more about this in like your 233 or 391 about how exactly virtual memory permissions are handled. But for us, we're just going to think about program data, program globals, stack, and heap as just uniquely allocated sections with different permissions. So the stack, like what we just talked about, NX, not executable, has just read and write permissions. Heap is the same. Program data, because we have code in here, we have to be able to read and execute. And then static globals, which are ones that don't change, is read only because we're not changing them. So then the question is, can we ever have write only permissions? And the answer is no. Modern processors, we can, if we have write permission, we can also read, because it doesn't really make much sense that we'd be writing memory, which we don't read. So like one mitigation we could do here, remember before how we were just sort of overflowing down the stack directly down past everything to update our return address? What if we put a value here that we check before we return to see if somebody's just smashed through the entire stack? So what we do is we put a controlled randomized value right before the return address, and we see if it's been modified before we return. And if it was modified, we know that somebody's blown through the stack and modified all the memory, at least up to the stack canary. So we can't really trust what's in the return address because somehow somebody's blown through the stack. So mitigation to this is called address, or another mitigation, not to that, is called address space layout randomization. And the way that we can use this is called position independent, like executable code. So the way that code is normally loaded into memory is it's loaded into a fixed address without pi. But with pi, we make our code, the address that our code lives at, unpredictable. So all of the code can't reference like, oh, we know our code's at this address, so we'll go here. It's all randomized, so we have to do everything relative. So now what we can do is randomize the layout of our program memory, specifically where our code lives, and then we can load it into a random address. Because everything's like offset, it'll still work because we're not using absolute addressing. So like maybe for the first load, we get this one value. The next time we load our code, all the code starts at a new address, but everything's relative, so it all works out. So now we're going to talk about how we actually compose these exploits, right? So we might have small primitives that don't do everything we want at once, but we can build them together to build a more powerful exploit. So like in this example, maybe we have two different vulnerabilities in the program. One of them gives us an out-of-bound read that reads an important address to us. The other one gives us a write. And together we can make a code execution exploit. So these are kind of common building blocks for an exploit. So some of them are different types of reads, right? So like if we can do arbitrary read, which means read from anywhere, that's very powerful. Uncontrolled is a little bit less powerful, but like if we have maybe like an out of bounds read, so we can read a little further than what the array should let us read, we can start to read some data, but maybe not pick this at any address anywhere and read that. Write, we can do arbitrary write, which is very powerful, also known as like a write what where exploit, which means you can write any data anywhere. It's very powerful. And then there's two types of kind of uncontrolled writes, where you can write some value, maybe not any value, but some value to anywhere, or you can write anything to some specific addresses that might be, out of bounds, but not arbitrary. And then leak usually is like a read primitive, but there are other ways to do it. And this is necessary because as we're talking about earlier, the address space can be randomized. And we need to know where things are in order to do some exploits. So in PWN I, our primitives were arbitrary writes or uncontrolled writes with buffer overflows. But now we're going to give you binaries with more mitigations that are more secure, such as like ASLR, the stack canary, and non-executable stack memory. So now we need to be able to leak so that we can jump to randomized locations in memory. Maybe leak the canary so we can keep that in track. Because like what we're saying, if you modify it, the program will crash. And then we have to not like necessarily jump to stack memory if it's not executable, right? So these are some ways to bypass the negations we've been talking about so far. So for non-executable memory, well, we can't necessarily place our code into the stack anymore and jump to it. So what you can do is, this is called return-oriented programming. Come back for the next phone meeting for this. But you can use code in the standard library. So standard library has a lot of code in it. If you can jump to that, it might do useful things for you. Or different code in the target program itself. And to bypass the stack canary, we'll need to leak the stack memory in order to get what the canary's value is. Or if our exploit doesn't blow through the stack for whatever reason, there's other ways to overwrite different types of code pointers. You can use that as well. And to bypass ASLR, we need to leak some pointer to the programmer's stack memory so that we can infer what that randomized offset is. Because if we know what the base address is, and then we get a leak or what the address is in our current execution, we can easily calculate the offset to infer how it was randomized.
Okay. All right. So dangerous function of the day, printf. Last phone meeting, we talked about gets and fgets with overflows, but today we're going to be talking about something that seemingly seems harmless, but you might have used this before if you ever programmed in C. You've implicitly used this if you've done like streams in C++. These are formatted print functions. So I'm able to provide it a string and I keep these little like digraph characters of like a percent and then a letter. And what that tells printf to do is like, hey, look into my other argument and shove it in there as the full string and print that out to standard out. So, I have hello %s Kevin prints hello Kevin. So I'm able to, dynamically change what that second string is, and this will always print out hello and then that second string for me. %s is for strings. We also have %d, which is for signed integers. So you can say my favorite number is 1337, and of course it will convert that out to the whole string on its own. And you can provide as many as you want, and as long as you provide the arguments for it, it will slot them in just fine. So, you can provide %s and then %d, and then it will look for the next two arguments, put those in, format as a string, print it out, lots of stuff. So these are format specifiers. These will try to look for arguments to replace itself with. There's also %p, which is pointer. There's like a table of like 20 of them you can look at in the man pages. So the question is, the first argument is a string. So what happens if we just use it as if a print function with some variable? So printf name. Now, if name is controlled by the user, we can run into a problem, because if it prints Kevin, or if the name is Kevin, it prints Kevin, that's fine. But the issue is, if we provide a format specifier, because we know we input a format specified string directly, now printf is going to look for stuff. And this is because printf is a rare variety function. In C, you can define functions that take an arbitrary amount of arguments, right? Because if I give you a string that has 15 format specifiers, it's going to look for 15 arguments. So what happens is it's going to look for a value after name. But if the code never specifies something, weird things can happen. So we have %p, which is our format specifier, and obviously if we put in the number, it's 1337, 1337, it prints it out in hexadecimal format, right? If I put it in 7, it would print out OX7. If I put in 13, it would print out OXD, right? But again, these arguments are located on the stack. Right, so as I call this function, I put these variables on the stack, and that's what they get loaded into, because this is how we call our functions. So after a certain point, these arguments are located. If there's enough format specifiers, it starts shoving them onto the stack, right? Because the x86 calling convention, you only include like the first 6 arguments onto your registers. Everything else gets shoved onto the stack. So once I have enough format specifiers, printf will look at all the regs for the first few format specifiers, because that's how we call functions. But past that, we start putting them onto the stack. So the question becomes, if we just provide a bunch of format specifiers as our string, where are our variables? And so it's undefined behavior. And specifically, it's a very unsafe behavior, because now what happens is we can put in all of our pointer registers, and eventually we'll start reading data off of the stack. And so %p prints out as little endian values. So that like your string is going to come out in reverse. So if that like the SIGPwny string is going to show up, you're going to see 73, 69, 67, so on. These are hexadecimal ASCII values. So printf, if used without having the right number of arguments with too many format specifiers, we get arbitrary reads off of the stack. And the way we can do that, especially if our input length is limited, is the fact that format specifiers are extremely feature rich. Because what I can do is include a number and a $sign before the type of specifier. And what that does is, please look at the argument 3 entries down. So printf doesn't even necessarily require you to use the format specifiers in order. You can ask for the third argument. But of course, if you don't have the third argument, now you can just print any index off of the stack with a high enough n. Sure, that's fine. So, our format specifiers can read from the stack, and our name variable is also on the stack. So eventually, with a large enough n, we'll just print out the address of our buffer. And that can be useful for many different things. All right. So to get a full arbitrary read, what we can do is have our buffer include this, n $s. We need some padding because our arguments are 8 bytes, so we want pad up to 8 bytes, and then we include our address. And the reason this works is because it's going to look for name, but then %s takes a string, right? So if I did %p, it would print out the number as in pointer format, but %s looks into the pointer. So I can input, some text, some padding, and then my address, and then it'll go like, all right, I need to read the string pointed to by this data, and then print that out at the front here. So then I get an arbitrary readout because %s reads these things out. So I can develop with %p, %n $p, to find which is the right n that gives me my own name buffer again. And then when I want to actually read out the value, I switch it over to $%n $s so that I can actually do the read. So printf, very, very nice function. It prints out these strings, and of course, if the main format string is controlled by the user, lots of bad things can happen. Now, clearly, the gods above who wrote the GNU spec would not make a function that both can read and write to a variable, right? It's a print function. Surely it doesn't just write to some variables. But of course, we've added the %n format specifier, which, God help us all, allows us to write the number of bytes that we've printed to some variable that we've included in printf. So now we get an interesting kind of way to write numbers to a certain variable. So we have an integer that is printed out but then used for logic, right? And we still control the format string. We can overwrite that number with something new using %n, because what we can do is if you include a number without the $, just a number, it will pad it with 500 spaces. So I can be like, all right, print out, let's say I know the address of something, print out, a couple million spaces and save it to this number. And suddenly that number might point to an address. So I'm able to write almost any number of bytes, provided that, the output of printf isn't truncated in any meaningful way. So again, we do the same thing. We can develop with %n $p to verify that the correct address is printed, and then use %n $n to then write to that address when we don't know where it is. Also to note that %n will write 4 bytes out, so it writes a 32-bit integer to its location. You can provide size specifiers called half and half to write 2 bytes or 1 byte. So if you have several printfs, you can get really specific with what you want to write and how many times and to what address. Okay, so that's printf. Any questions? Cool. So let's talk about libc. So libc is what holds printf, but also holds all the other fun functions that you use when you write things. It's effectively a program that gets loaded at the same time as the rest of your program, but it doesn't have any main routine. It just, well, that's a lot. It sort of has a main routine, but it's really just a giant collection of useful functions to use. So if with a printf vulnerability, we're able to get a leak to libc, suddenly we now get the locations of useful functions that we can use to run as executable, because we can't just write code and put it on the stack. We have to jump somewhere that's marked as executable. And libc, because it is the standard library, has useful functions to jump to. So we're gonna talk about raw in Pwn 3, but there's a stopgap that is simple to understand. There's a tool called OneGadget. And what OneGadget does is it looks at libc and it goes, hey, where do I need to jump to so that it calls execve bin sh? Because there is a function in libc that will just open a shell. It's called system. And if you jump to a specific location within system, if you have certain constraints that are enforced, if you jump to that location, you'll just pop a shell. No work needed to build a rock chain or any of these complicated things. So you can look up OneGadget, you can throw the libc of a program into it, and it'll tell you, hey, jump to this offset in libc, and you should get a shell if everything goes well. So that's it, printf. Our next meetings is just this Thursday. We're doing title jails with Cameron and Louis. Challenges. So I kind of revived most of the archives related to printf. So format 0 through 3 is just like kind of like using format specifiers to do interesting things. Execute is a shellcode writing challenge that has NX off, but format has NX on, I believe. libc ROP will probably need OneGadget to solve correctly. So be ready. These are kind of like on the harder end. These are just available and like pertaining to this meeting. And of course, our meeting files. Okay. All right. Awesome.